Hey nerds! Can we build artificial gravity? Or is the question, when will we build it? Now, we know that it's essential for living beyond Earth, but after a century of theory and decades of testing, we still haven't actually built a system that we can use. Meanwhile, science fiction solved it way back when. On the Enterprise, people stroll through corridors with coffee cups that never float away. On the Ross and gravity comes from a magically efficient engine that just never runs out of fuel. And on the Death Star, we don't talk about it. It's fine. Just why are you asking? In fiction, gravity is a background setting. It's the lighting panels, it's the air. There might be a switch for it somewhere, but we don't talk about it until we need it for the plot. In reality, though, for us, we're still waiting for the first ship where the crew can simply stand and walk. Gravity isn't something you can project from a panel in the floor. It's the geometry of space-time itself. But there are ways to fake it. Ways that work with the physics we already understand. Now, to see how, we have to start with the real thing. What is gravity, and why can't we just make more of it? If you're new here, I'm Abby, I'm a physicist, and I like nerd stuff, and I like teaching you guys about the physics behind the nerd stuff, but like in a way where we can appreciate and love the sci-fi that it comes from. We're not here to like criticize it or just shout about why it's wrong. We're here to explore the solutions that they come up with. And is there anything like that in the real world? Or how close are we to those kind of really cool solutions and ideas and things that I love that they use in science fiction? So that's kind of my vibe. And if you like that, then you should consider subscribing. If you already subscribed to me and you want more content, then you can check out my Patreon, and every month you'll get an extra video related to whatever topic we are talking about. So, moving in to gravity. Starting with what is gravity? For most of human history, we didn't know what gravity was. Things fell down, planets moved, the moon just kind of stayed up there somehow. That was about as far as anyone got. Then in 1687, Isaac Newton changed everything. His law of universal gravitation said that every object with mass attracts every other object with mass. And the force of that attraction depends on how heavy those objects are, as well as how far apart they are. Now, the equation for this looks pretty simple, but it explained almost everything. It explained falling apples, planetary orbits, ocean tides. With Newton's equations, astronomers even predicted the existence of Neptune before anyone had ever seen it. Now, for more than 2 centuries, gravity seemed like it was pretty solved. But there was one thing that Newton couldn't explain: how the force worked. You see, 2 objects separated by millions of kilometers somehow tugged on each other instantly. And there was no medium between them, there was no delay, it was just this action at a distance. Newton himself really didn't like this, and he famously wrote, "I feign no hypothesis," which is kind of like 17th century speak for like, don't ask me how, the math just works. Then Einstein came along, and he rewrote the idea from scratch. In 1915, his general theory of relativity said that gravity isn't some mysterious force pulling things together at all. It's geometry. Mass and energy bend the fabric of space-time, and that curvature tells objects how to move. Now, the classic picture that we all are probably familiar with seeing is like the bowling ball resting on a stretched sheet. Drop a marble nearby and it rolls towards the ball, not because there's an invisible force pulling it in, but because the surface itself is curved. The marble is just following the straightest possible path through a distorted landscape. Now, this analogy is only like a shadow of the real thing because space-time bends in 4 dimensions, not 2, but it captures the essence of what we're going for. Gravity isn't something acting in space, it's the shape of space itself. Now, Einstein's equations didn't just sound good, they worked. They explained small anomalies that Newton's laws couldn't, things like the tiny wobble that's in Mercury's orbit. They also predicted entirely new effects like light bending around massive objects and clocks running slower in strong gravitational fields. GPS satellites have to correct for Einstein's time dilation every day, or their position data would drift kilometers off course. Gravitational lensing, this is where galaxies bend the light from other galaxies behind them. This is one of the most spectacular confirmations of relativity ever photographed. So after like 100 years and lots of testing, general relativity remains our best description of what gravity is. And that's where the problem begins for artificial gravity. Because if gravity is curvature in space-time created by mass and energy, you can't just turn it on with the machine. Like, there's no dial marked 1G. But there is a way to fake the experience of gravity, to make your body feel it without bending space-time. And that's where the story starts to get interesting. Because the moment you take gravity away, the human body kind of starts to forget how to function properly. Microgravity looks fun until you live in it. On the International Space Station, astronauts float for months at a time, sleeping in bags strapped to walls, learning to pour coffee through straws, and drifting from one experiment to the next. Now, it looks effortless, it's cool to watch, but the body that evolved under 1G kind of starts to fall apart. You see, gravity isn't just what keeps you on the floor. It's part of how every system in your body knows which way is down. Bones, muscles, blood vessels, even the inner ear all rely on that constant signal of weight and resistance. When you take that away, the body starts to reprogram itself for a world where down no longer exists. Now, the first thing to go in this situation is mechanical load. Without gravity pulling you into the ground, your bones no longer feel stress, and stress is what keeps them strong. The cells that build new bone slow down, the ones that dissolve it keep going. So each month, astronauts lose 1 or 2% of bone density from their hips and their spine, which is the same rate as severe osteoporosis on Earth. Muscles follow this pretty quickly. On Earth, even standing still requires effort. In orbit, every movement is easy. Your big postural muscles, like your calves, your thighs, your back, they shrink because they no longer need to fight weight. After a half a year, even the most disciplined exercise routines cannot stop it entirely. Then, the heart changes. In space, it doesn't have to push blood uphill, so it starts to weaken. Blood volume drops, vessels in the legs constrict, and the moment astronauts return home, gravity hits the body like a shock. If they stand up too fast, the blood will pool in the lower body while the brain runs out of oxygen and they'll faint. This is a problem known as orthostatic intolerance. Meanwhile, fluid inside the body starts to redistribute. With no down, blood and tissue fluids drift upward. Faces swell up, sinuses clog, and pressure builds behind the eyes. Now, over weeks, that pressure flattens the back of the eyeball, distorting their vision. The body functions, but it's living in the wrong environment. It's tuned for gravity, but it's running in a place without it. Now, that's a lot of stuff happening to an astronaut's body, but it is fine for short missions. I know it doesn't sound like it is, but 6 months in orbit is manageable. The recovery will take a while, but you can handle it. But a crew heading to Mars, well, they're going to spend close to 2 years between Earth's gravity and microgravity, long enough for every system that depends on weight to drift far away from its baseline. Now, exercise can delay the decline, but it can't replace the continuous feedback loop that gravity provides. If we look at sci-fi for a minute, The Expanse imagines what that looks like in the long run with the Belters. They're born and raised in low gravity. They grow taller, they're lighter, they're fragile. When they visit Earth, their bodies can't cope. Now, it's fiction, so it's completely exaggerated, but it gets pretty much the foundational basis of it right. Gravity isn't optional. It's a condition for human life. And that's why for any serious journey beyond Earth, the question isn't just how we get there, it's how we bring gravity with us. Now, science fiction has been trying to solve that problem for decades, often by just skipping the hard part. Science fiction handles gravity differently depending on the story, as well as depending on how accurate they want to be and how easy of a life they want to have. Now, in most big universes, gravity's just another ship system. On Star Trek ships, the answer is of course gravity plating, panels in the floor that produce 1G across every deck. Since anything with mass or energy contributes to the curvature of space-time, and what we feel as gravitational acceleration is just objects following the geometry that results, if we wanted to create 1G the way the Enterprise does, you'd have to reproduce the same space-time curvature that the Earth's entire 6 by 10 to the 24 kilograms generate at the surface. There's no way to pack that amount of energy or that amount of curvature into a few square meters of gravity plating. Even if you could somehow concentrate the equivalent mass into the floor, the density would be so extreme it would destroy the ship. There'd be nobody walking on it. This is where gravitons often get invoked. Now, it comes up a lot in fan discussions as well as some of the pseudo-technical lore that we see in some of the manuals. But gravitons, they're not a Star Trek invention. They are a genuine theoretical idea from attempts to quantize gravity. In quantum field theory, every fundamental interaction has a carrier particle. So photons for electromagnetism, gluons for the strong nuclear force, W and Z bosons for the weak force. If gravity can be quantized in the same way, and we don't know if it can, its carrier would be the graviton. It would be a massless spin-2 particle traveling at the speed of light, coupling to energy and momentum. Now, if that picture is right, what we call a classical gravitational wave is just a collective excitation made of an enormous number of gravitons, the same way a radio wave is made of many, many low energy photons. The problem is, of course, scale. You see, gravity is crazy weak compared to the other forces. Like, it's insanely weak. 2 electrons will repel electromagnetically, something like 10 to the 36 times more strongly than they attract gravitationally. That's 10 followed by like 36 zeros times weaker. That weakness makes individual gravitons effectively undetectable by anything that we have. Now, at this point, some stories take a different route. Instead of trying to bend space-time directly, they change the thing that causes the bending, the mass. So could we change mass? Well, no. Mass isn't some sort of a dial that you can just turn. For fundamental particles, mass is set by how they interact with the Higgs field. Now, on top of that, most of the mass of ordinary matter doesn't actually come from the Higgs field at all. About 95% of the mass of protons and neutrons is the binding energy from the strong nuclear force. So it's like the dynamics of the quarks and the gluons that are happening inside the nucleon. So to adjust mass, you'd have to manipulate not only the Higgs field, but also the underlying dynamics of quantum chromodynamics. That is, you'd be reaching into the strongest interaction in nature and changing how it works locally.
Surely nothing is immovable.
Amy, this is like explaining gravity to a chicken.
So whether it's gravity plating, gravitons in a beam, element zero, you keep running into the same issue. You're trying to change one side of Einstein's equations without paying the cost on the other side. Now, as fiction, that's all completely fine. I'm totally cool with it. I have no issue with it. These devices exist so the characters can stand upright and we can concentrate on the story. From a physics point of view, though, it's beyond speculation. They require entirely new layers of interaction that we've seen no sign of anywhere in the universe. In our reality, if you want people to be able to walk around on a spaceship without floating, you don't get to cheat the curvature or the mass needed. But let's not lose hope. We're only at the start of the video. There's one more thing that sci-fi does a lot of that might bring us a little bit closer to reality. And that's, if you can't bend space-time, stick yourself to the floor. Use magnetic boots. Now, they're a staple of some of the more grounded space stories. So they're used in The Expanse, of course, and For All Mankind. It's not magnetic boots, but 2001: A Space Odyssey, they Velcro to the floor. Obsessed. Anyway, the idea is pretty simple. Rather than creating gravity, just use something to stick you to the deck. This way you can then walk around, you can orient yourself, you can, do your job. It feels pretty plausible, and it looks really cool, and it sounds really cool, and they click in.
There you go.
Now, as far as physics goes, it's real. In terms of electromagnetic adhesion works, you could build these today. And astronauts on the ISS have actually used some magnetic restraints before in small ways. So for storytelling, it works. And it's a really good bridge between the completely fantasy out there stuff and the reality. The thing is, magnetic boots, still not gravity. Gravity acts everywhere in your body at once. It's loading your bones, it's tugging on your organs, it's telling your system which way down is. It keeps your blood flowing the right way. That constant uniform pull is the background condition that your body evolved under. Magnetic boots only act where they touch metal. So it's the base of the boot and the floor. That's what's being grounded down. The rest of your body, it's still feeling like it's in free fall. Everything inside, all the stuff, your heart, your blood vessels, your inner ear, they all still don't have any sense of down. So while it looks like you're walking around biologically, you're still weightless. So in that sense, magnetic boots are more of a psychological fix, not a physiological one. They let you move naturally and they let you do your job, but they don't stop the slow unraveling of the human body in weightlessness.
Now you just walk around like you're in pumps.
How do you know what it's like to walk in pumps?
I didn't always work in space.
But they do give us a really good turning point in storytelling. Instead of inventing impossible forces, we're starting to work with ones that we do already have. And that brings us to Einstein and the moment where artificial gravity becomes real physics. If we can't generate gravity, we can still feel it if we move the right way. Now, Einstein worked that out in 1907. He imagined a person sealed inside a small room with no windows. You drop an object and it falls. You stand on the floor and the scales reads your normal weight. Everything behaves as if you're on Earth. But that room doesn't have to be on a planet. It could just as easily be inside a rocket accelerating upwards through space at 9.81 meters per second squared. That is the value of Earth's gravitational acceleration. From inside, there is no experiment that would tell you the difference. And that's the equivalence principle. The idea that gravity and acceleration are physically the same experience. Now, it's the core of general relativity, and it gives us the simplest way to make artificial gravity: constant acceleration. If a ship maintains 1g of thrust, the crew inside feel 1g of weight pressing them down toward the rear. That way, the bones stay loaded, the muscles stay active, the cardiovascular system keeps pumping uphill. For the body, it's indistinguishable from Earth's gravity. Now, there are tiny differences, like on a large ship, the nose would experience slightly less acceleration than the tail, but at human scales, you'd never notice. Now, The Expanse, which I'm bringing up again, yes, handles this almost perfectly. Its ships accelerate halfway to their destination, and then they flip and they decelerate the rest of the way. But down is always toward the engines. It's one of the best descriptions of gravity in sci-fi, but the limitation it has is energy. You see, you would need continuous energy to provide a continuous thrust, and that is a staggering amount of fuel. Chemical rockets manage minutes of burn. Ions drives can run for months, but they're at like millimeters per second squared of acceleration, thousands of times weaker than gravity. In The Expanse, ships use the fictional Epstein drive. That's an unfortunate name these days, isn't it? It's a near-perfect fusion engine that can burn for months at a steady 1G. It's plausible engineering, not entirely magic, but it's far, far beyond anything that we can build right now. So this idea, the thrust idea, acceleration, works perfectly in theory. Einstein's equations says it should, biology agrees that it would, nothing about it breaks physics. It's just that right now we don't have the engine for it, which leaves us with one other method. If constant thrust is too expensive, which it is right now, here's another way to fake gravity. You spin the ship. In a rotating spacecraft, everything inside experiences what feels like a downward pull towards the outer hull. Now, this isn't a real force, it's inertia. Your body wants to keep traveling straight while the floor keeps turning underneath you. From your point of view, inside the rotating frame, the resistance feels exactly like gravity. The physics is actually pretty simple here. The apparent acceleration is determined by A equals omega squared times r. Here, omega is the angular velocity and r is the radius of the rotating section. So to simulate 1G, which is 9.81 meters per second squared, you can either spin really fast at a short radius, or you can build it much bigger and spin slower. The smaller you make the system, the faster it has to spin, and the stronger the side effects become. Those side effects are mainly called the Coriolis forces. It's like this apparent twisting that you feel when you move in a rotating frame. So like you turn your head or you stretch out an arm and the motion seems to curve around you. Your system insists that the world is spinning one way, but your eyes are saying that it's moving another way, and the mismatch makes you feel nauseous, and it happens pretty quickly. Experiments, though, suggest that most people can actually tolerate up to about 4 rotations per minute with some training. But lower is always going to be better. Now, for long-term habitation, you want a radius of at least 50 to 100 meters to keep motion sickness and disorientation within acceptable limits. And that leads to 2 basic design philosophies. You've got the small-scale approach, spin only what you need. It's really efficient to do it this way. Only the living space spins, not the whole ship. But it does mean that you need mechanical joints that pass like power, air, data between spinning and stationary sections. And the crew have to move safely through those interfaces. Now, it's doable, it's just more complicated. The much larger scale approach of this is you spin everything together. And that's the idea behind O'Neill cylinders and Stanford Torrey. Enormous space habitats that are kilometers across, spinning to provide a steady 1G at the rim. You'd live on the inner surface under an artificial sky, with sunlight reflected in from mirrors outside. Now, the physics works really well here. The challenge is construction. Millions of tons of material, precision balance, the sheer logistics of building something like that big in orbit. The good news, though, is that none of this is speculative physics. Rotation works. It's been tested, it's been modified, it's been demonstrated in orbit. Back in 1966, Gemini 11 briefly tethered its capsule to a spent rocket stage and then spun the two around each other. The resulting gravity was teeny tiny, like about 100,000th of a g. But it proved the point. Rotation produces weight. So while we've never flown a crewed spacecraft with sustained artificial gravity, we absolutely could. The equations are settled, the materials exist. The main challenge now is engineering scale, not like scientific mystery. So we can't build gravity generators, and we can't sustain 1g of thrust for months at a time. But we can build a rotating spacecraft today. All that's missing is the commitment to do it. And that brings us to the next question. If we know it works, and we know we need it, why haven't we built one yet? So we've known for a century that rotation can simulate gravity. What we haven't done yet is live in that sort of a space station. And this is where the research happening today comes into it. We have short radius centrifuges, spinning the people, not the ship. Instead of rotating a whole spacecraft, you can just rotate the crew for short periods each day. So a small centrifuge, basically like a rotating bed or a chair, can create gravity at the feet while leaving the rest of the spacecraft untouched. NASA, ESA, and other agencies have been testing this for years now using bed rest studies. Volunteers, I don't know how they do this, volunteers lie in beds tilted 6 degrees head down for weeks or months at a time, simulating the fluid shifts and unloading that happen in orbit. They can't stand up, they can't lift their heads fully. Over time, their bones release calcium, the muscles shrink, and the cardiovascular system weakens, similar in ways that it happens in microgravity. Then they start doing the countermeasures. So some volunteers will stay motionless as a control group, but others will then spend an hour or two a day on a short radius centrifuge. The results of these tests are pretty promising so far. Daily centrifuge sessions maintain muscle tone, they seem to preserve heart function, and they do seem to slow bone loss as well. Now, it's not a perfect substitute for real gravity, but it is much better than none at all. Most of this work happens at ESA's ENVI-HAB facility in Cologne. It's a fully enclosed research habitat where participants live for months under constant observation. NASA and other partners run parallel studies then using identical protocols so the results can be compared directly. So if they're doing this, the next step is pretty obvious, right? Take one of these centrifuges off Earth. Back around 2009, ESA and the Japanese Space Agency actually did plan to fly a human centrifuge on the ISS. Astronauts would pedal a stationary bike while they're spinning, but the vibrations from the moving mass would have actually shaken the station's structure, and so the project was eventually cancelled. But the concept isn't dead, because several of the new commercial space station designs, such as Axiom, VAST, and Orbital Reef, they are already including centrifuge modules in their plans. So that means the first true human tests of artificial gravity in orbit could happen within the next decade. What's missing isn't technology, but necessity. Now, until we attempt missions that truly demand long-term gravity, so months to Mars or years beyond Earth's orbit, there's kind of little incentive to build something so complicated. And look, realistically, you guys, should we be building something like that right now? Is that what the world needs? Soon enough, we are going to be returning to the moon. And so for the first time, we'll be able to study what partial gravity does to the human body over months instead of just a few days. And that leads to the central question behind all of this work. How much gravity is actually enough? So artificial gravity sits at the intersection of physics and engineering. The principles are really well understood. We know how to simulate weight through motion by spinning a structure or by accelerating. And we can calculate exactly what conditions would reproduce 1G. What we don't know yet is how much of that load the human body actually needs. Somewhere between 0 and 1G, there's like a threshold, a point where bones stop dissolving and muscles stop fading and the cardiovascular system stabilizes again. Now, if that threshold is low, then maybe the moon's 1/6 gravity is enough. If it's a bit higher, Mars at 3/8 G could still work. If it's close to full Earth gravity, then every long-term habitat and deep space mission that has people on it will have to create its own gravity through rotation or thrust. They're the only two ways we're doing it. And that's what the current research is really trying to pin down right now. On the ISS, variable gravity centrifuges are spinning rodents at different G levels for months at a time. On the moon, the Artemis cruise will eventually give us the first human data from extended life in 1/6 G, and those results will tell us whether artificial gravity is a design choice or a medical requirement. Once that threshold is measured, everything else becomes a question of construction. How large a habitat needs to be, how fast it needs to spin, or how fast can it spin without making people sick. Science fiction treats gravity as effortless because it has to. Characters need to walk around, they need to eat, they need to argue on the deck without wondering what the Coriolis force is doing to their inner ear. In reality though, our first true artificial gravity will be mechanical. A rotating module, a tethered pair of spacecraft, a centrifuge that hums and vibrates as it turns. It's not going to look like science fiction's sleek corridors, but it will be the first step toward carrying Earth's pull with us wherever we go. Gravity isn't just what holds us down. It's part of what defines the world we come from, and it's the thing that we'll have to rebuild before we can live anywhere else. You guys, I can't believe I'm about to say it. It's just an engineering problem. I never get to say that.
That may be impossible, sir.
Things are only impossible until they're not.
Yes, sir.
Okay, that's my take on artificial gravity. We did warp drive last month, which I basically just shattered everyone's dreams and told you all it was never going to happen. So I wanted to bring you something that I'm like, well, it can happen. It can't happen the way sci-fi wants it to happen, but you know, that's storytelling. But this is something that we can actually do, and these are open questions and things that people work on, and some of the research in the studies is really cool, and it is really exciting that this is like a thing. So I just wanted to tell you a little bit about what's going on, about like where the limitations are and where we can go. So I hope you enjoyed it. If you have any thoughts on what you would like me to do next, please do comment and let me know. I'll pop a poll up at some point with a few options on there, but I have some ideas of what I think I should do. But you guys let me know. Let me know what you want. Let me know what you're into. For this month's Patreon video, to accompany this, I think what I'm going to do is I'm going to talk about gravitational time dilation, and I'm going to talk about Miller's planet in Interstellar, because I have some things I want to discuss regarding plot holes. For one of my favorite movies. Let's be honest, it's one of my favorite movies. It's one of the best science movies. I absolutely adore it. But there's a black hole there that I'd love to chat about. So that's what will be happening over there. I will of course be releasing a version of this video as a series of shorts if people prefer to consume things in short form content, or if you want like a little refresher on just different sections, then that'll be popping out over the next while. And last month I did a Q&A on the warp drive video, and I kind of really liked that. I thought that was a cool thing to do, so I'm going to do that again. But I'm not going to do it in 2 weeks' time. I'm going to do it in 3 weeks' time. I'm going to give you like 3 weeks to really kind of digest and all that kind of stuff. And yeah, so the questions that you have, start dropping them now, and I will start collecting them together and do a little Q&A in a couple of weeks. Thanks for hanging out with me. Sorry I talked quite a lot there at the end. I've talked quite a lot the whole bloody video. I mean, it's the point of it, isn't it? Okay, I'm just going to sign off now. Thanks for sticking with me, and I hope you enjoyed it. Stay nerdy.